Hi, I'm Chris Fiebrick, and I'm going to talk a little bit about soil moisture data and products from an in situ perspective, and more about how Mesonets around the nation measure soil moisture with some specific examples from the Oklahoma Mesonet. To start off with a little bit of background about the Oklahoma Mesonet, we are jointly operated by Oklahoma State University and the University of Oklahoma. And the reason I thought it might be important to point this out is because it's similar to a lot of the statewide and regional networks across the US. Not all of them, but most of them are operated by universities. This is the layout of our sites across the Oklahoma Mesonet. We're spaced about every 19 miles, which is approximately on the mesoscale. It's a scale that allows us to detect medium-sized weather events, for instance, fronts and outflow boundaries and things like that. About half of our Mesonet sites are on privately owned land, where a landowner has allowed us to put the site on their property, and the other half are on publicly available land. This is what a typical Mesonet station looks like. They're oftentimes a 10-meter tower. Reason for the 10 meters is so that we can put the wind speed and direction up at the top of the tower. 10 meters is the official WMO height for wind speed and direction around the world. And then along the tower, other measurements: air temperature, relative humidity, pressure, solar radiation, rainfall, and then the soil temperature and soil moisture measurements also. Now, with the various Mesonets around the US, there are a lot of different brands of sensors used. This is showing just a sample of the various sensors. There are manufacturers like Campbell Scientific, Hydroprobe, Aclima, ThetaProbe, and others. These are just some examples. Not only are there different brands of sensors, there's also a couple different soil moisture parameters that are used amongst the various networks. So when we talk about soil moisture, it could mean matrix potential or volumetric water or fractional water index or even plant available water. So it's important to understand the differences between these various soil moisture parameters that are measured. And a little bit more on the layout of Mesonets across the US. This is a map from the National Mesonet Program to show you that we have a great coverage of statewide and regional Mesonets across the US. Now, not all of these Mesonets record soil moisture data, but many of them do, and I believe most all of them are working towards making soil moisture measurements in their networks. There's a lot of value, as you can imagine, to having the soil moisture data co-located with the other measurements from a Mesonet tower like rainfall, relative humidity, temperature, and estimates of evapotranspiration. One of the things that we strive for as Mesonets across the US to try to set us apart is our emphasis on data quality and reliability and completeness. So we do a lot of work with calibrations, quality assurance, and we want to be able to deliver services in near real time. So there are a number of other measurements being made, for instance, by field experiments or research projects and the like, and those are, of course, very valuable. But as Mesonets, we want to have that real-time, complete data flowing in order to document climatic conditions over the long term. So to give you an example of some of the products we have in the Oklahoma Mesonet, this first one is Fractional Water Index, and it's derived from our matrix potential measurements. And Fractional Water Index essentially goes from 0, which is wilting point for the plant, up to 1, which is field capacity, meaning that the plant has unlimited access to water. And so we make these products, update them throughout the day, indicating that fractional water index at 2 inches, 4 inches, 10 inches, and at 24 inches based on the sensors we have at those specific depths. We also create 7-day changes in fractional water index, which help us look at whether the state's moistening or drying, if drought is intensifying, and the like. And then graphs of the time series of the data also. Now, to convert that data into a product that maybe a grower or producer could use, we also generate plant available water data. And with these, we are integrating the observations over the 4-inch depth, 16-inch depth, and 32-inch depth. And that corresponds with some of the various plant depths, whether they're seedlings or shallow rooted plants and deep rooted plants. So in order to generate these estimates, we took soil cores. Oklahoma State University did the analysis with the water retention curves so that we could estimate how much water is in that profile. And so then we have this set of plant available water maps, again integrating that 4-inch depth, 16-inch depth, and 32-inch depth. And then we also compare that to what the soil profile indicates would be the maximum water that integrated depth could hold. And we can create percent plant available water maps also. And then this is an example of the time series data. Our network takes soil moisture observations every 30 minutes, so we can plot those over the course of a day, weeks, months. And so what we've got plotted here is the 5 centimeter time series in red, the 25 centimeter in yellow, and the 60 centimeter in green. And we can see that with a half-inch rain event that happened last fall, it moistened the 5 and 25 centimeter depths. Those fractional water index values jumped up to close to 1, which is saturated. But then it took a 1 3/4 inch rain event before the 60 centimeter depth responded and was able to moisten and become saturated. One other note on this time series graph, this goes through into February, the big Arctic outbreak the southern Great Plains had, and temperatures well below freezing, which caused our soils to freeze at 5 centimeters. And because of that, our quality control removed those observations because the sensors didn't perform correctly when the soils were frozen. And then we do try to validate our estimates of soil moisture data. In this example, we looked at the state that was in at a period when it was in drought conditions. So it was somewhat of a controlled situation where all the soils were dry and we had a big rain event move in. And we then looked at how much the plant available water increased at each site compared to how much rain fell. So the 1-to-1 line would mean that 1 inch of rain fell and the plant available water increased by 1 inch. But of course, that's not necessarily the case. A lot of the data is below that 1-to-1 line, indicating that the rain that fell didn't necessarily all go into increasing the plant available water. Some of it ran off, some of it drained and infiltrated through the column, which makes sense. So all in all, these were some good findings to give us confidence in our estimates of plant available water. And then lastly, some limitations of soil moisture measurements from Mesonets. There's a lot of variability, of course. If it rained more at our Mesonet site than it may have in your area or in your field, we'd get different soil moisture values. Also, our measurements in the Oklahoma Mesonet are made under vegetated sod. So if your field is bare, that could change the infiltration and the soil moisture there. And then lastly, the soil structure could be different at our Mesonet site and in your area. So those are some of the considerations to make when looking at mesoscale soil moisture observations. And I'm happy to take any questions during these sessions, or you can email me at febrick@ou.edu. Thank you.